name is David Wayburn, and I will be presenting a short PowerPoint slide movie of some of my research results. What I want to discuss is a popular scaling parameter developed by Mark Zagarola and Alexander Smits of Princeton University. It has shown good success at scaling the turbulent velocity profile formed by fluid flowing along a wall. A fluid like air flowing over a plate or wing is interesting in that as the fluid flows over the plate, the velocity at the surface is reduced to zero due to friction. And as we move further from the plate surface, the velocity slowly transitions to the bulk inlet flow velocity. This thin velocity profile layer is called the boundary layer. It turns out that under certain conditions, the boundary layer will turn turbulent with bursts of random flow close to the surface. This turbulent motion causes an increase in the drag on the plate or wing. Hence, there has been a lot of interest into understanding this phenomenon. The Zagarola and Smits scaling parameter allows one to predict the evolution of the turbulent boundary layer. It has been cited in over 600 journal articles. What I want to talk about today is some research that I have done that indicates there are some serious problems with the ZS scaling parameter. Okay, let's get started.
Thanks for tuning in. The results presented today are based on the journal paper referenced here. So, let's set the scene. Here we depict a fluid flowing from left to right as it encounters a thin flat plate. The plate and the flow extends in and out of the plane in the plus minus z direction. A boundary layer develops along the plate in the flow direction such that the velocity is zero at the surface and gradually transitions to u sub e at the boundary layer edge. When we refer to the velocity profile along the plate, we mean the velocity u at x for all y. If the flow velocity is high enough, then the flow will transition from laminar to turbulent flow at some point along the plate. The question we are interested in is whether, under certain conditions, the turbulent flow velocity profiles at different points along the plate are similar. By similar, we mean, is it possible to find simple stretching parameters that make the scale profiles from station to station look similar to the extent that if we plotted the scale profiles on the same graph, they would overlap each other and appear identical? Let u sub s be the velocity profile stretching parameter and delta sub s be the thickness stretching parameter. These scaling parameter values vary along the flow direction but not in the y direction. The formal definition of similarity in mathematical terms is therefore expressed by this equivalence equation. Similarity is an important conceptualizing tool. It allows us to predict the evolution of the fluid as it flows along the plate. There has been a sustained effort in the literature to discover the similarity conditions and similarity scaling parameters for various fluid flow situations. It turns out turbulent flow over a plate is particularly difficult because it is not possible to use a theoretical path since closed-form solutions to the flow governing equations do not exist for this case. Hence, what has happened is that different groups have proposed various scaling parameters and then tested these parameters against experimental profile datasets to see if the profiles display similar behavior. In 1998, Mark Zagarola and Alexander Smits from Princeton University developed an empirical velocity scaling parameter for the outer region of the turbulent boundary layer that has been cited in more than 600 articles. For flow along a plate, the Zagarola and Smits scaling parameters are given by u sub zs and delta sub 99, where delta sub 1 is the displacement thickness. Now, delta sub 99 is a pretty obvious choice for the thickness scaling, but the choice for the velocity scaling is not so obvious. After extensive testing, a number of groups have shown good success with this scaling combination. In fact, Castillo, George, and co-workers have concluded that most turbulent boundary layer datasets display similarity using U sub ZS and delta sub 99. So, how do you explain the success of the Zagarola and Smits scaling? Well, to begin, we note that the fluid flow community prefers to work with the defect profile rather than the velocity profile itself. The way this defect velocity profile is calculated, you take each data set and find the asymptotic velocity value at the boundary layer edge, which we call U sub E. We then DC shift each data set by subtracting this asymptotic U sub E value from each data point. Please note that each shift is only dependent on the U sub E value for that data set. There is no external data involved. This fact will become important shortly. Now, back to the reason for the ZS scaling success. Let's take a look at an example. Here are 10 profiles taken from different measurement stations at the Princeton University's Gas Dynamics Lab wind tunnel. Taking the raw data and scaling with the ZS scaling does indeed result in the appearance of similar behavior. All 10 scale profiles using the ZS scaling parameters are plotting on top of one another, indicative of profile similarity. Okay, now back to the reason the ZS scaling works so well. This is something that I worked out recently. Consider the area under the curves. Mathematically, the area under the curve is given by the integral of the curve. Doing the math shows that the area under the curve for the ZS scaling always normalizes to 1. So as long as the shape of the velocity profile does not change from station to station, then the curves should plot on top of one another. However, it must be emphasized that this same shape requirement means that having equal areas is a necessary but not sufficient condition to ensure similarity. The ZS scaling has been shown to work remarkably well. So what is the problem? Why should we be cautious about using the ZS scaling? Well, the origin of this cautionary account started not long ago when I was plotting some of the turbulent boundary layer data sets and noticed something peculiar. I noticed that in the cases I examined, the data sets that showed similarity when plotted as defect profiles did not show similarity when plotted as velocity profiles using the ZS scaling. It was the same data, the same scaling, but one showed similar behavior and the other did not. This bothered me. How could performing a simple DC shift of the data change the physics of the flow? Performing simple mathematics on a data set should not change the physics. Something was not right about this. The DC shift was completely determined at each measurement station. There was no external data involved. But somehow the shifted profile showed similarity and the unshifted data did not. It bothered me to the point that I sent in a letter to the editor just expressing this apprehension that something did not seem right. Well, multiple reviewers and editors responded by indicating that I did not understand that the turbulent boundary layer was special, that for laminar flow you looked for similarity using the experimentally measured velocity profiles, but for the turbulent boundary layer you worked exclusively with the defect profiles. So, the apparent resolution to my quandary was that I should ignore the experimentally measured velocity profile as not important. I was literally told that by one reviewer. Of course, this response essentially saying don't worry about it bothered me even more. I decided to check into what is so special about the turbulent boundary layer. So, I searched the literature to find out why the turbulent boundary layer physics is special. There must be a very good reason why we are told to ignore the scaled velocity profile and concentrate on the defect profile. Unfortunately, a search of the literature reveals nothing. There's not one single paper, not one book, that lays out the argument as to why the defect profile should be used rather than the experimentally measured velocity profile. If that is the case, why has it become embedded in the flow community's accepted paradigm of turbulent boundary layer behavior? It appears the only reason for it is that it works. It is hard to argue with success. We may not know why, but it just works. We have visual proof. Just look at these profiles. But does it really work? After studying this problem much more thoroughly, I think I have an explanation as to what is really going on. Consider the two mathematical definitions of flow similarity, the one for the defect profile and the one for the velocity profile. By inspection, we see that the two must be equivalent if u sub e divided by u sub s is a constant as we move down the plate from station to station. This constraint should look very familiar to anyone that has studied the theory of turbulent boundary layer similarity. It just so happens that every theoretical treatment of defect profile similarity that has been published in the literature has as a requirement for defect profile similarity that u sub e divided by u sub s must be a constant. Check Rota's equation 14.3, for example. Okay, this is a critically important point. Please pause this presentation and go check out these references for yourself if you are not familiar with these papers. Verify that this really is the case. So this is a requirement for defect profile similarity. Having equal areas under the curve is a similarity requirement, but so is u sub e divided by u sub s equal to a constant. Well, if that is a similarity requirement, then we must conclude that defect profile similarity can only occur if velocity profile similarity is already present. You can't have defect profile similarity without velocity profile similarity. Yikes, somehow this point has been completely missed by the turbulent flow community for the last 60-some years. You cannot have defect profile similarity if velocity profile similarity is not already present. The bottom line is that there's nothing special about the turbulent boundary layer. There's nothing special about defect profile similarity. It still comes down to velocity profile similarity. The physics of the flow evolution along the plate is buried in an experimentally measured velocity profile. Good to know. But how has this important point been overlooked for so long? To understand how this might have happened, we look back at Fred Clauser's early work on scaling of the turbulent boundary layer back in the 1950s at Johns Hopkins University. Clauser is apparently the one to start the use of the defect profile in the search for similarity in experimental datasets. He was the first to show that whereas defect profiles from different groups collapsed to a single universal profile, the velocity profiles did not. In fact, the defect profile similarity theoretical papers by Rota and Townsend appear to have been published in direct response to this observation. Hence, subsequent searches for similarity scaling parameters for the turbulent boundary layer have adapted the use of the defect profile as a means of discovering similar behavior. So what the flow community saw was visual proof that the defect profile similarity was superior to the velocity profile similarity, just we have already shown. So this somewhat obvious similarity equivalence argument has been completely unappreciated until now. Okay, we have visual proof that the defect profile approach to similarity works, and the velocity profile approach apparently does not. But that does not remove the fact that U sub E divided by U sub S is a similarity requirement. The question is, did Zagarola and Smits check to see if this requirement was satisfied? And the answer is no, they did not. They had visual proof of similarity. Why bother checking? They did not check, but we will. Let's reconsider that data set we looked at earlier. Theory tells us that U sub E divided by U sub S is a defect profile similarity requirement. You cannot tell if this condition is met by looking at the scaled defect profile plots, but you can tell from the scaled velocity profile plots. The quantity U sub E divided by U sub ZS is evident from the tail of the velocity profile plot, right? Out here in the tail, U at xy becomes U sub E by definition. So, looking at this scaled data, it is evident that U sub E divided by U sub ZS is not a constant as required by the flow governor equation analysis of Rota, Townsend, and others. The ratio values are not the same, but instead are jumping from about 6 to 6.6. So in spite of the defect profile plot results, we must conclude that overall this data set does not satisfy the requirements for similarity using the ZS scaling parameters. Many other groups have also made claims of similarity based on defect profile plots. Here's an example from the Castillo and George paper. Does this data set show similarity? Looking at the defect profile plot, Castillo and George said yes, it does. However, looking at the wing of the velocity profile plot, the answer is again no, it does not meet the requirements of similarity based on their own theoretical derivations. Check Castillo and George equation 9. It basically comes down to the velocity profile plot. If the velocity profile plot does not show similarity, then similarity is not present no matter how good the defect profile looks. Let's look at some more data. Here is some superpipe data used by Zagarola, Smits, and co-workers to demonstrate defect profile similarity. Does this data set meet all of the similarity requirements? Again, the answer is no, it does not. The reason Zagarola, Smits, and others have missed this point is that it is simply not possible to tell whether all of the conditions for similarity are met by looking at defect profile plots. Having equal areas as demonstrated by defect profile plots is a necessary but not sufficient condition for similarity. Every theoretical flow governor equation approach to similarity also requires that U sub E divided by U sub S must be a constant. Of the more than 15 data sets I have cross-checked from the literature that claim similarity based on looking at defect profiles, none of the replotted data sets showed similarity in the outer region of the velocity profile plots using ZS scaling. Hence, one must be very cautious when using Zagarola and Smits similarity parameter together with defect profile plots to claim similarity in turbulent boundary layer data sets. So, that is the main takeaway here. Now, a second important takeaway is that defect profile similarity is not special. The turbulent boundary layer similarity is not special. Theory indicates that you cannot have defect profile similarity if velocity profile similarity is not already present. My observation is that the use of the defect profile invariably leads to the wrong conclusion about the presence of similarity. Hence, I suggest we forget about the defect profile similarity and go back to concentrating on similarity of the experimentally measured profile, the velocity profile. Okay, we're almost done here. One further takeaway is that based on my cross-checking results, I will go so far as to say that the present paradigm that most turbulent boundary layer data sets display similarity when plotted with the ZS Similarity scaling parameter is probably not correct. Instead, what I think is the case is that turbulent boundary layer similarity is rare and difficult to achieve in wind tunnel experiments. Refer back to the experimental papers by Cautionary and Zagarola and Krogstad. They showed it was necessary to introduce elaborate nonlinear pressure gradients in the wind tunnel to produce turbulent boundary layer similarity. This is not something that has been seen in most setups in wind tunnel experiments to date. Hence, our expectations should be that turbulent boundary layer similarity is rare. Okay, that's it. Thanks for tuning in. This is obviously a huge departure from accepted doctrine. I am rowing upstream on this one. Hence, I would really like to hear any comments or suggestions. If you think I got it wrong, please point it out and I will try to address that as a follow-on video. Please send your comments or suggestions to the email listed here. Thanks again. Goodbye.